I'm going to talk about some work that we've been doing in storage systems using machine learning to improve different aspects of the storage system is an exciting area. And we're going to talk about a specific technique that uses reinforcement learning for data placement. But this is an area that's very much under investigation. There's a lot more to do in this area because some of the choices are very difficult to make for humans, in our opinion, but machine learning can do this much better. This work appeared at ISCA last year. You can find more information. Let me start with an executive summary, just summarize everything so that you can go to sleep afterwards if you're interested in doing so. So we're going to talk about hybrid storage systems. You have multiple different storage devices to provide high and scalable storage capacity at high performance. And if you want to design a data placement policy between different storage devices, you usually need to provide adaptivity and extensibility. I'm going to mention these in a little bit more detail. Adaptivity to workload changes and also changes in system configuration. And you want to be able to extend it to more devices without changing the policy much. So our goal is to essentially provide that, even though this says a lot of words, that's what we want to do essentially. And Sibyl, the mechanism that we're going to introduce, uses reinforcement learning to provide adaptivity, to provide all of these, including ease of design and implementation, hopefully with low computation overhead, but we're going to incur some of the overheads of reinforcement learning. And key results are going to be good. There's always room to do better. We evaluate this on real systems, real hybrid storage devices. I'm going to show that in a little bit. And it improves performance by more than 20% compared to the best previous data placement technique that we know of. And in a dual hybrid system, if you have 3 SSDs, then you get even higher performance improvements. And actually, it's difficult to design a policy that considers 3 devices or 4 devices or 5 devices. So increasingly, this could be more beneficial if you're increasing the diversity of devices that you use. And we show that Sibyl achieves 80% of the performance of an Oracle policy with some storage overhead, as you can see over here. And this is completely open source. You can try it on your own, improve it, give us feedback. We're very open to that. So let me jump into what are the key shortcomings that we see in prior data placement techniques. So if you look at a hybrid storage system, it looks like this. You have a fast device and a slow device, and you may have more of these, of course. And they're managed by the storage management layer, which essentially acts between the host and the pages, right? So you get reads and writes, and then the storage management layer decides where to send these reads or writes to, where to place the data, etc. So there are a lot of decisions over here that the management layer may make, for example, promoting from the slow device to the fast device or evicting from the fast device to the slow device. And as an extension, I think you can think of like far storage as an extension to this also. This is something we're working on right now. How do you actually extend it to larger systems? Okay, so basically the performance of this hybrid storage system clearly highly depends on the ability of the storage management layer. How good are your decisions in terms of where to place the data? When you access the data frequently, should it be in the fast device? Probably yes, in terms of performance, right? But if the management decision is such that it's placed in the slow device, then you take a performance hit. So there are 2 key shortcomings that we see in prior techniques that significantly limit their benefits. One is lack of adaptivity, and this has 2 dimensions. They're usually not very adaptive to different changes in the workload. And the second dimension is they're usually not adaptive in the changes in device type and configuration. And the second is lack of extensibility to more devices. I'm going to show you examples of this with some numbers based on some case studies that we've done. So if you look at prior data placement techniques, they usually use a few workload characteristics. For example, how frequently you've accessed this block, right? That's one single characteristic. You may couple it with the latency or the cost of the block, etc. And then you can become more fancy. You can add more metrics. But then the problem is it's very difficult to manage all of these different characteristics with a human design policy, right? And usually the thresholds are statically tuned. If this block has been accessed, I don't know, 5 times, I'm just making it up, then migrate it to promote it to the fast device, right? Fast storage device. Now, if you compare these prior policies, one of them is heuristic based. The other is actually RNN, recurrent neural network based. Neither of these perform well compared to an Oracle. And in some workloads, they actually perform not so well because these workloads actually have a lot of changes in their access behavior to the storage. And we have a lot more analysis in the paper that I don't have time to go through right now. But this adaptivity to workload changes is important, and that's one of the things we're going to target. And the second issue with adaptivity is a lot of these policies are not adapted to change in device type and configuration. They usually do not consider underlying storage device characteristics. For example, when you change the level of asymmetry in the read and write latencies that you have between the fast storage device and the slow storage device, the policy may not perform well anymore. So here I show one example of this. You have two different hybrid storage system configurations. In this configuration, so here you have the normalized average request latency. Lower is better, of course. You can see that the CDE policy, which is one of the heuristic-based policies in the past, performs okay in this configuration, but it actually performs much worse than the baseline. Baseline is actually a very bad baseline, slow only. Place everything in the slow device. Fast device is non-existent. So you can see that this policy actually is worse than putting everything in the slow device in this configuration where latencies differ. So if you actually want to have a policy you've designed and you want to use it in multiple different storage configurations, this cannot adapt very well. You don't want a policy like this clearly, right? At least it should be as good as the slow only configuration, which is putting everything in the slow device, but it should be much better than that to begin with, right? So this is the lack of adaptivity, but there's also a problem with prior policies, which is lack of extensibility. Usually these are hard-coded heuristic techniques, which makes them rigid. And as a result, if you want to adapt a technique, if you design a technique and you design it for 2 devices, and you want to add one more device, one more level in the hierarchy, let's say in the storage hierarchy, it becomes very difficult to change these techniques. And we actually encountered this problem when we were doing this work. There are a lot of techniques that consider fast device, slow device. There's no, let's say, technique that is the best when you consider fast device, medium device, and slow device. So this is what we wanted to do. Basically, we want to have a data placement mechanism that provides adaptivity. And we believe that this adaptivity can come from continuously learning the application and the underlying device characteristics. And we also want to have easy extensibility so that we can incorporate a wide range of hybrid storage configurations that may not be, that you may not envision to actually use initially, but maybe you decide to incorporate into your system in the future. So our proposal is Sibyl, based on this picture. And the idea is to formulate data placement in hybrid storage systems as a reinforcement learning problem. Sibyl, by the way, is an oracle that makes accurate prophecies. We want to approximate that oracle. So how do we formulate this problem? So reinforcement learning is very interesting because all of us are reinforcement learning agents. We interact with our environment to make decisions. And based on what we learn from our environment, we change our decisions, right? So we have an agent. It could be a human. It interacts with the environment. It observes the state of the environment, and it takes an action. And then it observes a reward that comes from that environment based on that action. And then it changes the action to maximize the long-term or short-term rewards, depending on what you're trying to achieve in the end. So that's the idea. So clearly this was developed for humans, but also applied in machine learning successfully in many cases. You may have heard of AlphaGo, for example, and other AlphaFold more recently used for protein folding, etc. We actually use this for memory controllers, DRAM controllers in the past. And now we're actually very interested in adapting into other parts of the system. Basically, you have an action that learns to take an action in a given state to maximize a numerical reward, which could be a long-term reward. So there's a lot of theory behind it. So basically, we formulate data placement hybrid storage systems as reinforcement learning. Agent, in this case, our agent is a Sibyl data placement agent. It observes the features of the current request and the system by tapping into the hybrid storage system, which a storage management layer can do. Or you can add hooks that can enable this. And then the action is to select the storage device to place the current page that you're actually trying to access or allocate. And then we observe a reward. In this case, formulation of the reward is actually very important in reinforcement learning systems. In this case, we use request latency as a reward of the last served request because it encapsulates a lot of things in the storage system. But this is a subject that's really important that needs to be studied in the future, we believe. So let's take a look at these 3 components. Every reinforcement learning agent, you need to define a state. State is important because there are a lot of state features that you can examine, right? You can examine everything in the system potentially, but you need to do some feature selection. A limited number of state features is usually good in the sense that it reduces the implementation overhead because you need to keep track of these features. And we find that our RL agent is more sensitive to the reward function. but there's some dependence between the reward and the state, clearly. So in the end, based on feature selection, we have a 6-dimensional vector of state features that's detailed in the paper. One of them is the size of the request, for example, type of the request, etc., count of requests that you currently have, etc. And the capacity of the capacity remaining in the fast device, for example, is another feature that we use. And then we quantize the state representation to bins to reduce the storage overhead, because if you actually do this in a fine grain, your state space explodes, the representation space explodes. I'm glossing over a lot of details, but this goes into the design of the policy. And this is all open source, so you can actually find it and do it. Reward is the most important thing. This defines the objective of the data placement agent. And we formulate the reward function as a function of the request latency. And latency is nice because it encapsulates three key aspects of a storage system or storage device. The internal state of the device affects the latency. Read-write latency is affected. Garbage collection, when you employ it, how you employ it, affected. Queuing delays, they all basically affect your latency in the end. It's very hard to define a reward that considers all of these separately. That's why we actually use request latency that is affected by all of these. Latency is also affected by throughput of the device. Clearly, they're not the same thing, but it's affected. Latency is also affected by the promotions and evictions that you do. So it's affected by a lot of things. That's why we choose request latency, and there are more details in the paper. And then action is easier. This is the easiest one. Basically, at every new page request, the action is to select a storage device. Is it going to be the fast device or the slow device? And this action can be easily extended to any number of storage devices. And we learn, this agent learns to proactively evict or promote a page in the end. Okay, so let me give you the overview of how this is designed. The execution is decoupled in the sense that you have a storage request that comes from the system. It's a reinforcement learning decision thread essentially makes a data placement decision. Should this new thing be allocated in the fast device or the slow device, basically? And then there is an asynchronously running training thread that gets information from this decision thread, state, reward, and action information, and asynchronously trains a neural net. Well, I shouldn't call it neural network. Trains a reinforcement learning network, but we use deep learning as part of. We use deep reinforcement learning basically, and that thread periodically updates the inference network that is in the decision thread. So this asynchronous execution is important. Otherwise, training will be on the critical path, etc. And this is a more detailed overview of the Sibyl design. At the bottom, you see the decision thread over here. You have, let's see. Yeah, you have a storage request that comes from the operating system, and then you get an observation vector, which is essentially your state. And then using the state, we index into this inference network, which is essentially a copy of the training network that was copied in the past. And then the policy decides an action based on the maximum reward that it would predict based on the action that it's going to choose, and then decides to act on it on the hybrid storage system. And then it observes the reward as a function of the latency, as we discussed. And then it essentially updates this experience buffer with the reward and the state. So we collect all of the decisions that we make in this experience buffer, which gets transported to this training thread as a batch. So we don't do fine-grained communication between threads. We do batch updates. And essentially, this forms a training data set online while the system is running. And then this training data set is used to train this training network using reinforcement learning principles. And then periodically, this training network gets copied into the inference network so that we can hopefully get the best decision based on the recent experience. That's the idea. There's more detail, but you can find that detail in the paper as well as the source code. Okay, so now let me give you some results, and then we're going to conclude. So we have a real system with various hybrid storage system configurations, dual hybrid and tri-hybrid. This is our system, and you can see that the fastest device is the Intel Optane SSD, but we also have progressively slower devices over here, as you can see. And then we have a CPU. This is our cost-oriented. We evaluate multiple different types of configurations also, because in real systems, you have different types of configuration storage. This is a cost-oriented one. You have a low-end hard disk drive as the slow device. You have a high-end SSD as the fast device. And you have a performance-oriented configuration, which gets rid of the hard disk drive over here and replaces it with a middle-end SSD. And we evaluate this with 18 different workloads that are used commonly in prior work. You can find them in the paper. And we compare to 4 state-of-the-art data placement baselines 2 of these are heuristic based, and you can find more information about them in the paper. You may actually know of them. 2 of these are learning based. They're learning based, but they're not reinforcement learning based. They're more neural network based, and I think they don't do online decisions as well. So I think here, of course, you can ask the question, right? Why reinforcement learning? Why not neural networks? We believe reinforcement learning is a much better fit for this type of controller. And reinforcement learning actually incorporates neural networks internally as well. It's deep reinforcement learning, because reinforcement learning actually gets trained more easily based on the experience. And also it can adapt its decisions. Whereas if you train a neural network, then you're basically, you don't change your decisions based on experience. That's the beauty of reinforcement. And we applied reinforcement learning actually for DRAM controllers as well as prefetchers and CPUs, and we see good results for this type of decision making. Okay, now let me give you some results of our performance analysis. This is in the cost-oriented configuration, where we have a high-end SSD and low-end hard disk drive. And these are the policies that we compare to. Slow only is the worst policy, which you should not do worse than, in our opinion. Basically, you place everything in the slow device as if the fast device doesn't exist, right? And you can see that Sibyl outperforms all the baselines for all the workloads. This is the Sibyl, the red bar, and the Oracle is an optimistic baseline that ideally determines the best device to place a block in. So we're close to Oracle, and you can argue that this is not the best Oracle you can design, and you would be correct. So there are some limitations on the Oracle as well, because it's very difficult to determine based on like future execution what's the ideal decision to make. You have to look at a time quantum, and then Oracle is based on that time quantum. But still, it's not a bad Oracle. We cannot outperform the Oracle in most cases, but there are some anomalies that could happen in some cases. But you can see that the reinforcement learning agent is better than prior mechanisms. Now, if you look at the performance-oriented configuration, the story is essentially similar. This is more interesting because now the goal is performance, and all of these policies are designed for performance. Again, lower is better because this is the normalized average request latency over here. And we see that Sibyl is better than the prior techniques if you animate this. And compared to the best prior technique, it's about 21% better. Okay. And there are some cases where we're not better, and we discussed this in the paper. And in the end, Sibyl can achieve 80% of the performance of an Oracle policy that has complete knowledge of future access patterns within a time quantum. Okay, now the interesting thing is actually extending this to hybrid storage devices, which is a problem with prior mechanisms. It's not easy to extend the prior mechanisms to three storage devices. Extending Sibyl is relatively easy. You need to add a new action, basically, which is, as opposed to saying fast device versus slow device, now you have another option, right? And then we also add the remaining capacity of the new device as a state feature. So now we have high-end SSD, middle-end SSD, and a low-end HDD hard disk in this case. And we adapted, we actually came up with our own heuristic-based policy because none of the prior policies were easily adaptable to this hybrid storage device. And this is the average normalized request latency, and we compare Sibyl to that. And overall, we get much better performance in most workloads. There are some cases where we don't get better performance, as you can see. But on average, we get about 48% reduction in request latency. And I think the bigger benefit, well, certainly there's performance benefit, but this sort of mechanism, in our opinion, eases the architect's burden because you design one policy, and by making minimal modifications to it, it can be extensible to more devices as well as more workloads. So in the paper, actually, we have a lot of evaluation on the workloads. So how do you train this? How does it perform on workloads that you've never seen, for example? This actually performs much better than prior mechanisms for workloads that have never been seen because it can adapt to the workload by online learning. Okay, so what's the overhead? The overhead is there, but it's not too significant given the size of the storage devices that we have. You can see that the total storage cost goes into the experience buffer, inference, and training network. This is part of the storage device. And we get some metadata overheads per page that we need to have. Inference latency is about 10 nanoseconds, which is not bad, clearly. Training latency is much longer, but training is off the critical path. And again, you can accelerate these if they become on the critical path, of course. So we're right now trying to extend it to more use cases. So there's more evaluation in the paper. If you're interested in IOPS, you can see IOPS. Again, it provides higher IOPS. I mentioned the unseen workloads. I mentioned the mixed workloads, like heterogeneous workloads. It also provides similar performance benefits. And then we also look at different features. We can do automatic feature selection to decide which features to use. And hyperparameter setting is always a problem in machine learning training. And reinforcement learning is also famous for its hyperparameters. So we have some sensitivity studies for that. We also have sensitivity studies to the fast storage capacity and perhaps very importantly, explainability analysis. I mean, clearly you cannot explain completely what the decisions are because there's some black box inside there, especially the neural network, the deep neural network. But we try our best to do some explainability analysis, and there's some reason to think that this is actually making the right decisions for the right reasons, let's say. Okay, there's a lot more in the paper. You can find it on arXiv or on our webpage, and also the source code. You can check it out if you're interested. So let me conclude. So Sibyl is the first reinforcement learning-based data placement technique that we know of in hybrid storage systems. It provides adaptivity, easy extensibility, and ease of design and implementation. And we evaluated it on real systems using many different workloads and many different use cases. And we see significant performance improvements, as we've discussed. And we get 4/5 of the performance improvement of an Oracle policy with reasonable overhead, I should say. So there's more to do in this area. We are looking at, clearly we have looked at data placement, but it's not just about data placement. There's a lot of potential for prefetching, etc., and also tail latency improvements. That's something we're working on right now. And you can find the paper, slides, and videos, the video that is done by my student who has done the work. And I should also maybe put a pitch for our SSD course if you're interested in learning more about things like this. We have a lot of work on SSDs that we cannot cover over here, but we actually run this course, and it's live streamed online. It's open to everyone. People can participate and ask questions as well if they're interested. And we also have a computer architecture course. Okay, I'll stop here. Thanks for your attention. I'm happy to take any questions.